It's been a while.
Yeah, it's been a while. And we've moved in from next door, so that's
Yeah,
good.
much better office setup here.
Yeah. So,
Studio.
what have you got for me today?
More the other way around. But today I wanted to pick your brain on one of the most, I think, sort of unsung hero of modern technology. If you think about the big innovations over the last hundreds of years, you think of the internet, people probably think about AI today, of course, electricity, the railroad. But one that doesn't get a lot of credit is the relational database and how important that is. Obviously something very important to everything we do in building data architectures and whatnot, but really wanted to pick your brain on the history of the relational database and why it's so fundamental to kind of digital life today.
Cool. Yeah. No, I think let's get into it. Actually, I mean, it does sound. It's not a
Bored.
particularly exciting subject. People might not think, but
It is for us.
it is for us. I absolutely love a relational database, and I do just about come from a world pre-relational databases, so I've seen both sides, and yeah, it's really very cool.
Maybe before kind of diving into the relational database and SQL and everything it does for us today and has over the many decades, I would love to get your perspective on sort of how data was stored and managed pre-Edgar Cod, pre-SQL, pre-relational database. So it wasn't
So
so easy.
yeah, so I think I've told you sort of my first kind of brush with a computer when I was at school. The sort of the microprocessor came out, and the very early sort of home sort of systems like the Commodore PET were just about to sort of be launched, but schools didn't tend to have them. And what schools had would be normally a terminal that kind of connected via a phone line to a university computer. But we did have a computer in our school. It was made by Elliott Brothers in London. It was called a 903, and it was all transistor, and it had a whopping 8K of memory.
What would that, like contextually, what would that be the equivalent of today?
So, well, 8K means it can store 8,000 of its pieces of information. Its smallest piece of information, which is, we called it a word, which in that case actually was 18 bits long. So it's only 8,000 things in its memory. Whereas, on your iPhone, you think about when you buy an iPhone, they'll say, oh, it's a 32 gigabyte. So what's that? A megabyte is a million. So that's 32 billion, and the Elliott had 8,000. So,
Not exactly a
probably if you had an Apple Watch would be, we're talking about hundreds of thousands of times more storage than the Elliott had. But the Elliott, the one that we had at the school, the first thing that we used to do to put information in was a paper tape, a tape with punched holes in it, so that if we wanted to use a piece of software, a compiler, we'd actually put this paper tape in and run it through the machine, and that would load the compiler into the storage. But they did sell that machine with magnetic tape, which was, quite the thing. So people, I think, who used to use that as a serious sort of processing environment would have done everything around magnetic tape. And I remember visiting a data center, actually as a school trip. We used to have this thing called Field Day, and we'd go out and have these trips. And they had rooms of people who were putting data onto punched cards, the sort of pieces of cardboard about this sort of size. And these people would just, have papers, and they'd be typing it all in, and the punch cards, would come off these punches, which would clack, 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 very mechanical, very noisy. But those kind of cardboard cards, you could put them in a reader, and the printer, the computer would sort of scan them in. And yeah, I mean, memory was so small that everything really had to go onto a magnetic tape.
And how would you retrieve data in a magnetic tape? It's not exactly doing a query or a...
Well, so you're exactly right. So a magnetic tape would be, I think standard size was about 2,400 feet long. They could store 6,000 characters an inch, which is about 2 or 3 pages of A4. But if you wanted a record that was right at the end of the tape, that tape would go round and round and round very mechanically until you got to the record that you wanted. So we never had the concept of a query or a retrieval. And computer programs were written around sort of what we call batch processing. So it would be things like, let's run the payroll. And a tape might be put onto the machine, which, let's say, has all of the employees' records and their salary amounts, and maybe someone had punched into a card the number of hours they'd worked in that month. And the batch process would start with employee 1, and the tape would go around and just read employee 2, employee 3, employee 4, calculate all of the salaries, and then perhaps print out all of the pay slips on a great big printer. That it had done its job. But if someone went and said, I want to know all of the people who are earning more than a certain amount, the only way to get that was to write a program in something like COBOL or Fortran, where you'd basically read in each record, and then the programmer typically would know a record would be a block of information, and it would be surname, Christian name, date of birth, perhaps salary would be one of the fields. But the programmer would say, okay, so I now need to look at position, let's say it was 24 to 39 is where the salary is stored. And then, is that above what I want or not? And the whole tape would have to run through. So to get the answer to that question, a programmer would have to write a special piece of code, and then the whole tape has to go through. It's going to take you some days to get the answer to that. So the system was actually not used in that context. The idea of a query and just, finding the data was never part of it.
Absolutely.
Under that world of tapes,
For sure. And probably a significant room for error.
Significant room for, yes, because the poor programmer had to write a piece of code that actually did that. And what if they put a bug in there or whatever? Because you started everything from scratch,
And then Edgar Cod comes along, also known as the Codfather,
Oh, is that right? Is he called the car? That's
according to the
yeah.
Reddit lore.
Oh, brilliant.
And he comes out with a paper in 1970. I think it's called A Relational Model for Shared Data Banks. And as a mathematician yourself, I know there's some really brilliant innovation in terms of this idea of the relational database in that paper. It took a while to commercialize and sort of get right. But what was so incredible about his insight in that paper and sort of the maths behind this idea of a relational database?
Yeah, it's interesting because, I did actually write some programs around tapes when I was, younger, and then I became aware of databases and started to use them. I didn't actually read Codd's paper until probably only a few years ago. The first thing I'd say is it's a beautiful paper because it's written in a really clear style. And I must say, I would urge, if anyone's thinking of writing a paper, read Codd's paper because it's just really clear and really explains things. It's very accessible, really.
No ChatGPT writing.
No, so many papers now are, almost impossible to really understand what's going on.
For sure.
But he wrote a great paper. And yeah, what he came up with is really incredibly simple. So my example of having a great big tape of employees, let's say you wanted to write the department. On the tape, you'd write the employee name, and then you'd have to have some characters which say the department. Then you get to the next employee, you'd write the department. You'd write the department. The text that you're putting in is being repeated again and again and again and again on the tape, which actually could be quite error prone, because what if suddenly you decided to change the name of a department, but you updated some of the records and not others because of some bug in your code? Then half the people might be working for the new department name or the old one. It all just becomes a mess. And what the Codfather said was, if you've got a list of departments, write them down once. But of course, then you need to say, to which department is each of my employees? Well, don't write the department name. Write something that allows you to make a relationship, because we're now making relationals, constructions in data, which typically would be a small number. So department number 1, number 2, number 3. And of course, how many departments does a company have? A dozen? You don't need much of a number. And that immediately did many things.
Such as?
So on the tape, when you just kept repeating all those blocks of text, that's taking up space. If you just have to write little code number, that's absolutely tiny. So that's kind of really cool. Saves a lot of space. If you want to add anything to the description of your department, like maybe which office block they're in, or who is responsible for that, or what's their budget for the year, there was no real logical place to put that on a tape. Do you just put all of that information on the tape? But when you've just got a list of department names, you can just write those little pieces of extra information next to the department name. So it made it very logical to add new places of data. But then a brilliant part of this was making things so much more robust. For example, if you've got 12 departments, let's say code 1 to 12, and suddenly on your tape you find a 13 or a 14, that has broken the reference, the integrity of what the relationship is. Suddenly you've got some data. So what you can do is, when you build a database product, you basically say to that product, do not let anyone put information in this which will break the relationship. So then, and that's, when we're using a computer program these days, and suddenly it'll say things like, no, you can't check out because you haven't given me a credit card yet. It's enforcing business rules. Databases just do that naturally.
Absolutely. So you basically have 3 options: 1, 0, or null.
Oh, I didn't know if you were going to, this man's been studying the paper. He wants to talk about the nulls. You're really pressing the old mathematician's buttons now.
Well, I think it's super interesting just because, if you go back to one of the earlier videos we did, it was all about the math behind machine learning.
Yeah.
And one of the things that you say as sort of like a mathematician is some of that math's actually relatively simple or historical. It's been around for a long time. Simpler for you than me for sure. But it seems that with your take on sort of the relational database and Cod's paper, that it is relatively simple idea in terms of using relational algebra and whatnot. But we'd love to kind of understand why it is important to have the option of binary, 1 or 0, but then also why null is so important.
Okay, so yeah, I think this was interesting. And when I was telling you about this idea of, say, a payroll file, the file was actually designed for something that it really had a purpose. It needed to, let's say, run payslips. So you needed to have everyone's name, date of birth, and salary. So it was very dense. You didn't have gaps. It was quite unusual. You make sure you had all of the information before you added the record. But a relational database could start to think of the concept of, okay, we've got some of the information, but we've got gaps. Now you think about our modern life. This happens all the time. You sign up with Amazon and they'll say things like, we'll need your name and address and your email. And then, do you want to add a credit card now to your account, or do that later? I'll do that later. So what are they doing? They're saying, okay, there's a gap there. And it's allowing the concept of the unknown. But what I find interesting as a mathematician is, when you're doing a query, you'll often use Boolean logic. You'll say things like, tell me about people who are Portuguese and they're tall, or Portuguese or English. So you're using ors and ands to kind of form logical constructions. But what happens if I'm doing that kind of search and I actually haven't got someone's nationality? So what if we've got the case where the person is Portuguese and another person is, well, we actually don't know what do you do in that situation? And the answer is, normally computers are binary. You either have true or false. It's one or naught. Everything's two. But the relational database has this concept of it's one or it's naught or it's actually I don't know.
My permanent state.
Mine too, as I get older, I tell you.
Put it on my tombstone.
Yeah, you and me both. But yeah, so that's actually quite interesting. And I think, the database has kind of formalized how we deal with unknowns,
For sure.
which actually confuses an awful lot of people when they start using databases, because it does. When you have nulls in your data, it can really catch the unwary and start doing some funny things.
For sure. No, amazing. And then I think it took a little bit of time and more innovation for it to become kind of commercialized and sort of adopted across the board. And I think there were some other really incredible findings, like the concept of transactions and joins and the whole concept of ACID and whatnot. And wondering if you can tell me a little bit about that and why that's so fundamental to the technology becoming usable.
Yeah, it's nowadays, I think somebody wanting to write a database would be relatively, I wouldn't say simple, but operating systems have got so many things in them that would kind of help at the beginning of building databases that operating systems might not have had, the ability to just rapidly sort things and, at a low level. And so that kind of took its time. And so, as you're saying, actually being able to do joining data and joining data files and merges, that sort of takes quite a lot of time. The thing you referred to about ACID is so vital for transactions. We go to the bank. Let's say I put my card in and I'm going to take out 200 euros. And what if there's a power cut just at the point when I've pressed enter and it's about to give me the cash and the cash doesn't come out of the PowerPoint, out of the ATM? Is the database going to say, oh, no, you pressed commit, you pressed enter? Is there going to be a disconnect between what's on my statement? We gave you that money. Or did you? And the thing that the database controls is it has this concept of the A stands for atomicity. It's a single thing. So the whole transaction might be thousands of sub-operations, but the system will say, okay, I'm starting a transaction, and then it does all of the thousands, and only when it gets to an end is that then committed to the database. And so in that case where the power fails and the money didn't quite come out, the transaction never finished, it's not written to the database. So that's why we don't have those kind of errors. You never really, in a modern day transaction, find that, hey, they've said I took that money out, but it didn't come out. That won't happen because of these kind of functions in databases. It's really built into the database at a very low level that keeps it all very consistent and very accurate. And of course, we just rely on that for everything.
Yeah, so prevalent, like any transaction, bank transaction, any purchase and whatnot.
E-commerce, booking airline tickets. It just goes on and on and on. And I think none of us really think about it.
Or appreciate it, really.
Yeah.
Take it for granted.
Yeah, but it's all going on in the background.
Like electricity, it's prevalent everywhere. You can't even think about turning on a light switch anymore, but it's so fundamental. And that's why I think it's super interesting also just from a commercial context as well, because obviously IBM, produced this paper through COD, and then I believe their researchers also later down the line came up with the idea of ACID and transactions and whatnot. But ultimately, they were also very focused on their own database that was doing quite well, a hierarchical database in IMS, and making a lot of money, and probably stuck in a little bit of a innovator's dilemma.
Yeah, I was actually going to ask you about that because I remember you telling me this story, which I didn't really, appreciate, which was, and I found it quite interesting. Um, and actually, it did cross my mind that you might have actually seen sort of similar things in your career where, I mean, let's face it, IBM had the silver bullet.
Yeah.
They had it in the palm of their hands and they kind of played around with it, but it didn't work for them. And why do you think that was?
Making too much money from IMS. I think a lot of people didn't believe the relational database could actually work in practicality. Maybe a nice idea in a paper, but would it actually work in a bank or the government and whatnot? And it probably took a lot of time to kind of get to the level it needed to do to be something in that environment. But it's quite interesting because you think about a quote that I find very insightful from Satya Nadella, CEO of Microsoft. And they asked him, if you could have a get back on any technology in the history of the world that Microsoft could have been first to market with, what would it have been? The iPhone, the internet, cloud computing. He said the relational database.
Interesting.
Which is super interesting. And if you think about the origins of a company like Oracle, which started off as sort of a software development lab, that was literally their first name, Software Development Laboratories. They came across their co-founders and Larry Ellison, the kind of the famous Oracle chairman now, Cod's paper, and really believed in the idea. And then they came across subsequent papers that they had put out on SQL and really kind of believed that could work and went for it and ended up winning a contract with the CIA. Talk about a good use case for using and managing more information and leveraging.
And data that you don't know.
Exactly.
If the CIA is going to have holes in their data, they obviously they're going to have it.
And many hundreds of billions, if not trillions later, here we are today. So it's super interesting. And I think
so too.
I think it's relevant too to kind of appreciate how the technology works, because we also live in an age where everything's becoming so much based around natural language in terms of the computing and for interface with large language models and whatnot. And sometimes people treat a large language model like a database, but it's not. It's not necessarily going to give you a null unless it's been architected to do that. It won't say it doesn't know. It's architected to predict the next token and to potentially make something up. So I think it's super interesting to think about like decades old technology that's still so important today. And even when you're thinking about helping organizations build cutting edge applications with large language models, a critical factor to ground knowledge and to ground information.
Well, you think when you're selling into our customers, we very often start with a database because we'll want to see their data before we even put it into any kind of AI or any kind of training scenario. And we pretty often end with a database because people want to see reports and it's a database that really makes things like all the Power BIs and the reporting function. So even though we live in a very modern world of data science and AI and all of that, the database is always there.
Garbage in, garbage out.
Yeah, absolutely.
Brilliant. Well, appreciate the time. And
Oh my gosh.
looking forward to the next one. Thanks for this beautiful new studio.
Yeah.
And have Christmas cookies.
Oh, absolutely. I'm going to tuck into one of those in a minute.
Brilliant.
But thanks ever so much. No, it was a really good suggestion. I've really enjoyed it. So thank you.
Thank you, Johnny.
JTA Labs, a data-driven video cost experience.